Namaskar. Welcome you all in today's counseling session. The topic of today's counseling session is basically a red black tree. We will try to cover the introduction, insertion or creation as well as deletion operations on red black tree. So let me start. So after covering this topic, that is red black tree, the learners will be able to grasp two concepts, that is they will be able to learn the fundamentals about the red black tree, and apart from that they will also learn how to perform the operations, basically two operations, insertion and deletion operations on a red black tree. So let me start from the introduction and what is exactly the red black tree. So before we come to the red black tree, let me discuss from where it comes. Basically it is modified version of, we can say, AVL tree, and AVL tree which is a modified version of binary search tree. So we can say that AVL tree as well as red black tree both are modified form of binary search tree. Then the question is, what is binary search tree? So binary search tree, in fact, it is a binary tree in which a node may have maximum 2 children, 0 or 1 or 2 children. So in binary search tree, we know that if we consider any particular node of a binary search tree which is known as BST, so all the left subtree of a node contains all smaller keys, smaller elements, and the right subtree contains bigger or equal elements. So this is the basic property of binary search tree. And in binary search tree, we know that when we apply the traversal, we know that there are three methods of traversal: pre-order, in-order and post-order traversal. So when we apply the in-order traversal, then we get the keys or elements of binary search tree in a sorted order, in ascending order. So the advantage of binary search tree is that its a searching time is very less. If it is a balanced binary search tree or nearly balanced, then the time complexity of searching a keys from the BST is order of log n. So this is the best case time complexity. And if it is unbalanced, that is skewed binary search tree, then its time complexity is more than log n, and it may be in worst case order of n. When it will be order of n? For example, it is completely left skewed or it is completely right skewed. For example, if we create a binary search tree from a list of keys which are already sorted in ascending order, then in that case we will get a right skewed binary search tree. So in the right skewed binary search tree, if we want to search a key, then we will start from the root. We will follow to the next node because it is right skewed, so we will go to the right, then we will go to the right, and so on. So in the worst case, we may get the element at the last node. Similarly, if it is left skewed, completely left skewed, then also it will be order of n. So to reduce this time complexity, the two versions of modified BST came. And first is AVL tree, which is nearly balanced tree, in which we know that there is a balance factor of each node. So balance factor in case of AVL tree is either -1 or 0 or 1. That is, the difference of height between left subtree and right subtree is maximum 1. But the problem with the AVL tree is that to maintain the balance factor, there is required a lot of rotations, and that is the extra cost which is involved in case of AVL tree. So comes the red-black tree. So red-black tree is also a self-balanced binary search tree. Binary search tree means all the road toward its right are greater and toward its left are smaller. So it maintains a near perfect balance by coloring each node red or black. It is called a red black tree because all its nodes are either red or black, and they are also nearly balanced. Nearly balanced means that the difference between the smallest path of a node from root to leaf may be the difference between the smallest and the biggest path from root to leaf may not be the twice more than twice. So this is the first property, and there are many other properties. As I told that each of the node are either red or black, and the root of the binary the red black either black or red. Another property is that no two adjacent nodes must be in red color. In the red black tree, red, one may be red, another may be black, or both may be black. That is okay, but both may not be red. That is the third property. And fourth property is that every path in the tree, path means starting from the root till the leaf node. So every path in the tree have the same amount of black colored nodes. There should not exist any path such that the number of black nodes are different. It should not be there. So if all these four properties along with the BST property, binary search tree property, if these four properties are satisfied, then we say that it is a red black tree. Advantage of difference between red black tree and AVL tree already I told, because in AVL tree it is nearly balanced tree. So to make it nearly balanced tree, that is to make the balance factor 0, -1 or 1, we require a lot of rotations. So to avoid this cost, to reduce this cost, we use red black tree. So in the red black tree, multiple and faster insertion and deletion operation are made more efficient than the AVL tree. We will see, when we see the creation of red black tree, then we will come to know that how it is easier than AVL tree to make the insertion or deletion operation in the red black tree. So before we come to the operations here in this tree, so root should always be black of a red black tree. So here in this case it is black. And second property is that there should not be two consecutive red nodes. So in this one you can see there is no parent and child which are red in color. There are parent and child which are black, but no two consecutive nodes are red. And also the important property is that in each of the path, number of black nodes should be similar. So we can see that from root to the left node, we have two number of black nodes, and in all other nodes like 5 to 12 to 8 to 6, we have again two black nodes. Similarly, from root to 5 to 12 to 8 to 10, 5 to 12, then right 15 and 20, it also have only two black nodes. So that property is also satisfied. So each of the path have here maximum two number of black nodes. Though the null nodes, which are the it means the leaf node does not have any children, those are known as null node. They are by default assumes black nodes. And this example also satisfy the BST property, binary search tree property. How? We can see that all the node have smaller elements toward its left subtree and greater values nodes are there into the right subtree. Say for example, at the root we have 5, toward its left subtree we have only 3, which is smaller, and toward its right we have 6 elements. All the 6 elements are greater than 5. Similarly, when we consider say 12, which is right child of 5, so to this particular node 12, all the nodes which are toward its left like 8, 6, 10, they are smaller than this 12, and all the nodes which are toward its right are bigger. So in such way it also satisfies the property of the binary search tree. So all the properties are satisfied. That is why it is a red black tree. For example, if we add a new node, say 25, so 25, in that case where it will be inserted, because it should be a BST, so we will first go to the root. 25 is greater than root, will go to the right. 12 is also smaller than 25, so we will again go to the right. 15 also less than 25, so we will go to the right, and 20 is also smaller than 25, we will again go to the right, and the 25 will be inserted toward the as a right child of 20. And what will be, first of all, what should be the color of the newly inserted node? We will discuss it later on, how we can change the color to make it red black tree. But another property which will be violated if we insert 25 as a right child of 20 is that the difference between the length of the smallest path to its longest path is more than twice, because the smallest path is from 5 to 3, that is 2 nodes. And if we insert 25 to the right of the 20, then there will be 5 nodes which is more than the twice of the length of the smaller path. So in that case it will violate the properties of red black tree. So we will discuss how to do the changes to make it red black tree. So now I come to the operations. What are the basic operations which can be performed on red black tree? So first operation is basically insertion, which is also known as creation, because if the red black tree is empty, then we start from the root, and then one by one we keep on adding the elements and maintaining the red black property. And another operation is that of deletion, how we can delete an element from the already existing red black tree. So we will discuss these two properties, these two operations. So let me discuss first the insertion. So insertion operation in red black tree is similar to that of binary search tree. In binary search tree we know that how to insert a new node. We will compare the new node with the root. If it is smaller, we will go to the left, and we will compare to the left node. If it is smaller, then we will go to the left, and accordingly we keep on looking for the suitable location where we can add the new element. So it should follow the BST. And another is that apart from the BST, it should be BST, when we insert a new node, we also look whether it maintains the property of the red black tree or not. If it does not maintain the property after insertion, then we have to make it red black tree. That is, we have to do the changes, rotation or recoloring or whatever changes are required to make it a red black tree. So these are basically the steps which are followed. So there are basically two cases. The first case is that check whether the tree is empty. Obviously, when we insert the first node, the tree will be empty. So we will insert the first node. So check whether the tree is empty. If it is empty, make the current node as the root node and color the node black, because we know that in red black tree the root is always black. So first node when inserted, it will be root and as well as its color will be black. But when we are going to insert the next nodes, the root already it red. So initially we create a new node and make its color red. So by making these changes, there arises two different cases. The first case is if the parent of the new node is black. So if the parent of the new inserted is red, so it is not going to violate the red black tree property. But if the parent of this new node is red and the color of the parent sibling is either black, so for example, if the parent is red and new node is also red, then there will be two consecutive red nodes. So in that case, it will violate the property of red black tree. So what we will do in that case? So if the parent of new node is red and the color of the parent sibling means parent's child. So parent sibling is either black or it does not exist. So if it is either black or it does not exist, then what we do, we apply a suitable rotation and recolor accordingly. So there we apply the RR or LL rotations and recoloring is also done so that it becomes the red black tree. But if this is not the case, if the parent of this new node is red and color of the parent sibling is also red, then what we do, we recolor the parent, recolor the sibling and grandparent nodes to black. And the grandparent is recolored only if it is not root node. So grandparent is not recolored if it is root node. If it is not root node, then only it is recolored. Okay. So let me see example, then it will be more clear. So we have seen the cases which may arise when we start creating a red black tree. So let me see one example and see which of the case arises and how it can be handled. For example, we want to create a red black tree to insert these elements which are shown here in this slide in the order. That is, first 4 is inserted, then 5, then 8, then 10, 15 and so on. So initially when we insert 4, initially the red black tree is empty. So we will no violation of the red black property. That's okay. Then in step 2, we add the next node, which is 5. Because 5 is greater than 4, so it will be right child of 4 and its color will be red. So after inserting 5, the tree will become as shown in this particular slide. Here also the property of red black tree is maintained. First of all, it is binary search tree and then all the paths have the same number of black nodes and also there are no 2 consecutive red nodes. Now we is greater than 5, so it will be inserted to the right of 5 because it should maintain the binary search tree property. But here in this case, we can see that here it is not a red black tree. What are the reason why it is not red black? And all the path, the length of the smallest path and the longest path is more than the twice. The smallest path is from 4 to the left because there is no node to the left, so its length is 1, but the longest path, which is from 4 to 5 to 8, its length is 3. So it is more than twice. So this property is also violated. So what we will do, we will apply a suitable rotation and recoloring. What will be the rotation? In that case, it will be RR rotation, because it becomes unbalanced due to the 5. So we apply RR rotation, then 5 becomes root and 4 becomes its left child and 8 right child. So now it is BST, as well as it also satisfies all the properties of the red black tree. Now we insert the next element, that is 10. So in that case, because 10 is greater than 5, also greater than 8, so it will be inserted at the right child of 8. So here in this case, we can see that it violates the red black tree property. Which property is violated? There are two consecutive red nodes. So in that case, what we will do? We will recolor the which of the property is satisfied. Out of these, which of the property, which of the case arises? It is the third case. If the parent of this node is red and color of parent sibling is red, recolor the parent, the sibling and grandparent node to black. And the grandparent is recolored only where it is not a root node. So applying this case, we get this tree. So now after recoloring, we got the tree which is shown to the right side, colors, black color nodes, as well as is also satisfied the all other properties of red black tree and also BST. Now again there are two consecutive red nodes, 10 and 15, and we can see that here we will apply rotation, because the balance factor of 8 is -2. So we will rotate as well as recolor also. So along which we will rotate, again RR rotation will be applied toward its right child 8. Okay, so 8, and now the 10 will become the parent and 8 will become the left child and 15 will be the right child, and recoloring is done accordingly. So here after doing this, we can see that it is a now red black tree. Similarly, we insert now 18. So 18 will be inserted at the right child of 15. Again it violates the red black tree property, that is the parent sibling is red. Which case arises? The parent sibling is red. 18 is inserted, its parent is 15 and its sibling is 8. So the parent sibling is red. So we recolor the parent, sibling and the grandparent node. Since the grandparent node is 10, and because it is not a root, so we will do the recoloring of this also. So after doing this, we get this tree which is satisfying the red black tree property. Now we insert the last element, that is 25. So after insertion of this also, it violates the red black tree property. So in this case, the red parent node of this node is red. The parent node of this 25 is red, and since the parent sibling is null, we apply a rotation only and recoloring. So after rotating toward its node 15, we get this tree which is now satisfying all the properties of red black tree. So after complete inserting the last element, we can see that the final tree which we obtained, which is shown toward its right side, it is red black tree because it satisfies all the properties of red black tree as well as binary search tree. So today, in fact, we have, due to shortage of time, we have discussed only the introduction, properties of the red black tree, as well as how we can create red black tree, and when it violates the red black tree property, then how we can do the rotation as well as recoloring of node, so that ultimately the binary search tree becomes the red black tree. So that is all for today, and remaining, that is deletion, we will discuss in some another day. So thank you very much.